Okay, so I took Dirk's charge to talk about both carbon dioxide removal and solar geoengineering. And frankly, this is not the area I'm really focusing my time right now. Right now, my time mostly is focused on trying to help facilitate an energy system transition to a net zero or even just a real zero emission energy system. And so my focus these days is on energy system, but I've thought a lot about these things. And so I took this opportunity to try to collect my thoughts that I thought might be useful to you. And I should say that my context, what is my bias or my context coming into this, is that I kind of, first of all, I really love Germany. I've spent probably a year in Berlin over the last decade or so in different slots. And I kind of get the sense that often there's like a lot of negative feelings about both carbon dioxide removal and solar geoengineering by many people. And so while I want to validate the concerns, over the possible things that can go wrong with these things, I want to argue that there's enough value to them that we should be trying to understand and learn more about these approaches, even if we're skeptical about using them at scale. So anyway, no further ado, I'll just jump into the talk. So again, I also have to say that my feeling overall, I'm taking the opportunity to do a little pontification here. My feeling overall in a lot of the climate science community is that people, it would be really helpful for people to spend more effort arguing positively for what they think could lead to better outcomes. And there's enough headwinds that we're working against of people who just want to maintain the status quo that, for people to be attacking other people's approaches where they're maybe we don't like them so much, but we're not really certain maybe they would be helpful. That I think it's just we're making much more of a contribution by saying what we think would work and what rather than kind of constantly opposing things. And the other thing is, sometimes this falls into a funding situation of a zero sum, like, well, if we use resources for this, isn't that going to take resources away from that? And I think we just need to focus on getting a bigger piece of the pie. If you think of how the physicists have been really good at getting tokamaks and CERN built, and the community comes together and says, okay, let's as a community try to increase the size of the pie. So anyway, that's just a little bit of my bias coming in, and I'll just do another slide like that on the way out too. So I'm going to divide this talk into two sections. One is carbon dioxide removal, which is how I interpreted the negative emission technologies. And so I divided this talk into two pieces. One is basically solar geoengineering, and one is an overview of carbon dioxide removal. And basically, I want to just be clear on the distinction that carbon capture from power plants, while it uses many of the similar technologies in some cases, is outside the scope. This is really removal of CO2 that's already been released to the atmosphere. And this talk is going to be more on the conceptual issues, but there have been a couple of recent reports, and there's also review papers. But there was this 2019 National Academy report on negative emission technologies, and it has this. You can go to this website and download it for free. And so, really, if you want to follow up the literature, I'm not saying that's the greatest report in the world, but at least it has a good set of relatively recent citations. And then there was also another report just last year on ocean-based carbon dioxide removal and sequestration approaches. Again, it's available for free. And so just for more technical detail, I would say maybe not to go to those reports, but go to those reports and look at the citations and see what they say. So this is the summary from the first National Academy reports on negative emission technologies, and they really highlight 5 approaches. One is terrestrial carbon removal and sequestration, and this, I guess is things like afforestation, reforestation, biochar, various agricultural approaches. And, usually those ones often have a lot of co-benefits in that they can, improve biodiversity and things like that. They can also improve soil quality and so on. And so those things tend to be favored by many people. And the main problems with it tend to be issues of permanence and also verifiability. And, can you verify how much carbon was stored in this forest relative to what would have happened in some kind of counterfactual situation. Another one is biomass energy with carbon capture and storage. And this was very popular in a lot of the integrated assessment models. And the basic idea is that you burn wood or other biomass and then take that CO2 and capture it from the power plant and inject it underground. Another one is carbon mineralization. I'll go into that in a little bit, but the idea is to get cations, calcium or magnesium and things like that, react with CO2 and typically make calcium carbonate or magnesium carbonate. Direct air capture seeks to remove CO2 directly from the atmosphere, much the way plants do, but doing it chemically. And then typically the idea is to compress it and inject it underground in geologic reservoirs. Coastal blue carbon, to me, most ecosystems are in quasi-steady state, and I don't think they're really taking up that much carbon, but there's a lot of carbon in mangroves and other coastal environments. And for me, this coastal blue carbon is more about protecting existing carbon stocks and not so much about carbon dioxide removal, but it was still included in that report. On the ocean side, I won't take the time to go through all of these, but I think the one that's gotten the most attention maybe is ocean nutrient fertilization or ocean iron fertilization. There's also the alkalinity enhancement, which I'm going to talk about. First of all, I don't like to use the words enhancement. To me, that suggests a value judgment on it already. Another one is this kelp farms has been getting a lot of attention recently, the idea of growing kelp and sinking it. I can talk about all of these in more detail in the discussion, but I'm not really going to discuss them in more detail in the talk. So one of the things, I think it's unfortunate that carbon dioxide removal in its early, and I was involved in the 2005 report at the Royal Society in the UK that lumped carbon dioxide removal along with solar geoengineering, both in the context of geoengineering. And I think that was kind of a historical mistake in that I don't, let's say you had a coal plant or something emitting CO2 to the atmosphere. And, if we instead did carbon capture and storage and had that CO2 go into geologic storage, we would say, okay, that's mitigation. But if you have that same power plant emitting to the atmosphere, then you have another facility removing that CO2 to the atmosphere and putting it in the geologic storage. It's identical from the climate system perspective. And so to my mind, that carbon dioxide removal is just another way of reducing net emissions and just falls squarely in the mitigation category. And one of the reasons it got lumped into the geoengineering category in some things, there were these kind of dystopian stories of people creating the next ice age by removing massive amounts of CO2. And I just don't think that those kinds of stories are plausible in that, we're in a time when there's massive net emissions to the atmosphere. And, while lots of scenarios show us going to negative net emissions, I hope I see that day, or hope anybody sees that day, but I'm not holding my breath. So I think for the foreseeable future, carbon dioxide removal or negative emission technologies will be used to reduce net emissions and not to do any kind of climate control. I do want to say that some forms of carbon dioxide removal, in particular ocean fertilization, and you could also say large-scale afforestation, they do manipulate natural systems at large scales, and thus arguably, especially I would say the ocean fertilization could be considered geoengineering. But it's geoengineering because, in my mind, because it's manipulating natural systems at massive scale. And it's not geoengineering because it's taking carbon dioxide from the atmosphere. So I would just consider in the broad category of carbon dioxide removal as a mitigation approach aimed at reducing net emissions, and that there's some of these approaches that work through manipulation of natural systems at large scale that you could consider geoengineering, but the whole category isn't geoengineering, at least in my taxonomy, in my mind. So, and speaking of taxonomies, there's a bunch of different taxonomies, and I don't need to go through all these things, but people categorize these things in different ways that, that you can either, like Beck's bioenergy with carbon capture and storage, uses biological mechanisms to remove the CO2 from the atmosphere, whereas other approaches like direct air capture uses chemical techniques. And so that's like one way of categorizing these approaches. Another dimension on which they vary are distributed versus centralized. And, obviously, if you have a growing forest, that absorption of that CO2 is distributed, or if you fertilize the ocean, that's also distributed CO2 uptake. If you add alkalinity to the ocean, that's the distributed CO2 uptake. Whereas things like direct air capture, I guess, is maybe the only one where it's really a centralized facility, although Beck's obviously has a centralized capture and energy production facility. And then another major distinction is this a land-based approach or an ocean-based approach? And then other important dimensions to consider is the permanent versus impermanent. And I have to say, I think this is going to get more attention, I think, in the coming years. There's a lot of people who are developing permanent, let's say direct air capture with permanent storage, and they're, which is today $400, $500, $600 a ton CO2 or more. Meanwhile, you have people selling carbon offsets with reforestation or afforestation for $10 or $15 a ton CO2. And the people who have, I guess there's two perspectives on it. One is like, well, if these direct air capture are so expensive, then we shouldn't do it. And the other one is, well, it's really important to get that permanence, and we need to separate our consideration of types of negative emission technologies, so that the added value of the permanent storage can be reflected in the cost of, or in the price of the carbon storage. Anyway, different things. Some of these approaches store the CO2 as molecular CO2. Some of it is ionic in the ocean, and some is organic carbon, just burying biomass and so on. Okay, let's just go on to the next one. Okay, I think I covered this well enough. Let me just go to the alkalinity addition approaches, and this is the only one I'm going to talk about in any detail, just because it's one that I happen to like, even though I think it has its critical problems, but it's maybe one that's less well understood. So in the natural carbon cycle, if let's say CO2 comes out of a volcano, that CO2 will circulate around the oceans and will be absorbed by the biosphere. But in something like 100,000 years or so, it will eventually find its way into carbonate minerals. And the way that it does that is there's silicate minerals typically on land, and there's many different silicate minerals, but I'm just showing this one here as a simple representation. Basically reacts in the groundwaters, and really CO2 and other organic acids and so on are involved in this reaction. But the net of it is coming down the streams, you get calcium ions and magnesium ions and sodium and potassium and so on that are balanced by the hydroxyl ion and along with some silica. And so this goes down into the ocean, but then this calcium and hydroxyl reacts with the CO2 and forms calcium and bicarbonate ions dissolved in the oceans. And now this would happen naturally on the times, this part here. Oh yeah, so the other thing is there's a parallel reaction involving calcium carbonate. So this reaction, the time constant on it is, if you add a pulse of CO2 to the atmosphere, it will take around 300,000 years for that excess CO2 to be removed from this mechanism naturally. There's a parallel mechanism involving calcium carbonate that would normally take around, say, 4,000 to 10,000 years. And anyway, so there's two basic things that can happen with this. That it can either wind up in the ocean, and the good thing about this one is it does, that normally the bicarbonate from the CO2 is balanced by hydrogen, which is making the ocean acidification. And so doing this can basically both store CO2 and ameliorate ocean acidification. Oops. And then the other approach, which some people are talking about, is making solid calcium carbonate. Now, let me just say what the big problem is. The big problem is mass handling. That for each, a ton of CO2 is 44 grams. I think this is something over 100. And, then this is around 100 grams. So, you're going to have like 2.5 times more calcium carbonate than you had CO2, and you're going to need something like 3 times as much silicate minerals. You're going to do that mass handling both on the way in and the way out. And so anyway, to me, this whole approaches have real mass handling challenges and huge mining operation that you would need to do. You'd need to be mining cubic kilometers of material each year. And anyway, but geochemically, this is what's going to happen naturally. And these alkalinity addition approaches basically seek to accelerate what would happen naturally. But anyway, what we would like is something that's environmentally benign, scalable, that you could bring it up to the scale of the problem. I mean, one of the problems is right now we're emitting CO2 something like 100 times or 50 to 100 times more rapidly than volcanoes emit CO2 naturally in hydrothermal vents. And so, that we're so overwhelming what the natural system does that, it's hard to do something at small scale that's going to make a difference. And so, so there's a lot of things, that are might not be so bad, but you can't really do them at large scale, or maybe they're scalable and environmentally okay, but then it really only makes temporary storage, or it's not, or it's just super expensive. Like direct air capture, I think, is actually most in its best configurations could be all of these 3 things, but it's expensive. And so, and really, I don't think there's anything that meets all of these criteria. I would say that but some of them, have huge co-benefits. Let's say forest restoration is the clear winner, where you'd want to do that just for biodiversity and environmental protection reasons. And then if you get carbon storage, that's a co-benefit. Actually, I was talking to somebody yesterday, and we did a paper back in 2006 where we showed that if you cut down boreal forests, the Earth would actually cool. Because if you have a snowy field, the snowy field reflects a lot of sunlight to space. But if you have a dark forest, that the sun hits the forest and it gets absorbed and it warms up. And it turns out the warming effect from the darkness of these Arctic forests is actually overwhelms the cooling effect of the carbon stored in those forests. And so, people said, oh, well, does that mean we should be cutting down forests in the Arctic? And I said, well, to me, a lot of trying to mitigate climate change is to protect natural ecosystems. So it would make no sense to destroy natural ecosystems to reduce amounts of climate change. But it kind of shows to me, really, the environmental protection and the biodiversity benefits are really primary, and that to me the carbon storage is a secondary co-benefit. I think it's kind of a shame that just protection. I always felt if somebody cut down a forest, I did some work in the Mexican rainforest. I always felt like if somebody cut down a forest, the main insult environmentally is to that forest, and the distal harms are secondary. Anyway, so I think there's a real game theoretic problem with carbon dioxide removal, and that, if you, let's say in the electric power system, if you don't let people build coal plants or natural gas plants, they're going to build wind and solar and nuclear if you let them, just because they want the electricity. And so people benefit locally from these devices. And I used to think that the way that we would solve the climate problem is by having a universal carbon tax or a cap and trade. But at least here in California, well, there is some of that. It's proven a lot politically easier to kind of ban a technology or just regulate against the technology. And I know economists don't like that sometimes because they say it's not economically efficient, but anyway, in the case of the energy system, basically, if you don't allow people to build things that use the sky as a waste dump for its greenhouse gases, people will build versions of it that don't use the sky as a waste dump. But with carbon dioxide removal, it's all about local costs, and the climate benefits are distributed broadly in space and time. And so people are only going to do it if you have a system of incentives in place. In California, we've had trouble with forests where, people who never intended to cut down a forest bought a forest, would buy a forest, claim that they were intending to cut it down, and then get a carbon credit for not cutting it down. And, so there's all this stuff about figuring out what is the counterfactual. And then we've been having all these forest fires. So what if you buy a plot of land and you're saying you're saving the carbon on this land, and then there's a forest fire and now there's no carbon on the land? And, and so all of these problems of how do you monitor this, how do you develop a set of incentives, I think is a real challenge. Somebody was telling me a story about in China that they had built sulfur scrubbers on a lot of their coal plants, but running the sulfur scrubber was many millions of dollars every year. And it was basically cheaper to bribe the inspectors than to run the sulfur scrubbers. And so they had all these coal plants with sulfur scrubbers, and they just weren't using them. And so maybe in places with really good governance, but for a gigawatt power plant, the cost of the carbon capture and storage is going to be in the hundreds of millions of dollars a year. And to have governance institutions that can stand up to those kind of incentives to manipulate and game the system. Anyway, so I think there's a big game theoretic. Yeah, so basically, I think that carbon dioxide removal can basically work, and that the game theoretic challenges are maybe primary, but maybe that's just my bias. Yeah, so basically, my feeling is that mostly we need to work on decarbonizing our energy system. And, I happen to like nuclear. I know nuclear is not very popular in Germany, but, wind and solar. Wind right now is the lowest cost bulk electricity provider. There's people are coming up with means. I mean, right now I have an electric vehicle, so increasingly energy services are being electrified and so basically the electrify everything that you can, and decarbonize electricity system still seems to be the center stage. On the other hand, there are a few things that are hard to do, and one of them, let's say for air flights from New York City to Sydney, it really does look like liquid hydrocarbons are the best way to do that. Now you could get carbon from biomass. You can take electrolytic hydrogen and upgrade that carbon from biomass into a liquid hydrocarbon fuel and make a liquid hydrocarbons other ways. So I don't want to say that that direct air capture or something like that is going to be the cheapest way of allowing hydrocarbons to be used internationally, but I think it's at least plausible in some of our models, depending on your cost assumptions and so on, you can get direct air capture. And one of the reasons is, let's say, so to get 80% emissions reduction out of the electricity system, if you have natural gas backup, is relatively easy, because when the wind's not blowing and the sun's not shining, you can run your natural gas plants. And in most simulations, you can get rid of something like 80% of emissions that way. But, as you go further down, you still need some way to, fill in those gaps, energy gaps. And so, one way is to just have a gas peaker plant. But if that's only running a couple of times a year, and you try to build a carbon capture facility around that, you're only using that carbon capture facility a couple of times a year, whereas a small direct air capture facility could run continuously throughout the year and then offset the emissions from the gas peaker plant that gets used a few times, or or similarly offset the aviation fuel. But let me just say that I think there's a big difference between simultaneously offsetting, like, it's one thing to fly a plane from New York to Sydney using fossil hydrocarbons this year and simultaneously be removing that CO2 from the atmosphere through technical means. It's an entirely different thing to say, oh, we're going to fly this year and then future generations, decades from now, can take it out of the atmosphere. That's problematic to me. So just in the interest of time, I'm going on way too long. So I'm going to just jump past this removal summary and go on to solar. Again, I see I'm already a half hour into it. I was supposed to be done by now. So I'm going to just go more quick through solar geoengineering. Again, there's National Academy reports. You guys, you all have this talk, and you can get a copy of it and get these links out of it, or you can email me and I can send it to you. So yeah, just to say, there's a bunch of different approaches that have been suggested, but the one that really probably gets 80 or 90% of the attention, or should at least get 80 or 90% of the attention, is putting particles in the stratosphere to deflect sunlight back to space. And this basically big volcanoes have done this. Most recently, Mount Pinatubo was the volcano that did this, and then previously that there were several others in the last century. But basically the physics of this is well known. These other things, let me just not even discuss them today. So just to say that this is from this model into comparison project, but this is I think this is RCP 4.5 without solar geoengineering. This is with mean temperatures, and there's a little bit of overcooling of the tropics and overcooling of the tropics and undercooling of the high latitudes, but the amount of temperature change is greatly reduced. And again, the precipitation offset, this is actually precipitation minus evaporation, is greatly reduced. It's not eliminated, so it's not perfect, but the amount of climate change is greatly reduced. I won't go into this too much, but just to say that that CO2 suppresses precipitation and sunlight doesn't. And so basically, if you offset all of the temperature increase of CO2, you still have some of the precipitation. And so if you adjust to counteract all of the temperature increase from CO2, you end up with less precipitation. And so, but you could also just do less of the solar geoengineering and not offset all of the temperature, and then leave some of the, leave the hydrological cycle in better state. Yeah, so just to say, one of the things here is that, oh, there's winners and losers. And it's really not true, I don't think. I mean, it is true maybe in some level, but this is this is temperature extremes, precipitation minus evaporation, and then precipitation extremes. And again, this is what I said, if you just offset half the temperature, this is saying that, 100% of the people have their temperature change reduced and nobody has their temperature change increased. That maybe something like a quarter to 2/5 of the people have some improvement in the in the hydrological fields. And, there are a couple of people who, this is fraction of land surface, but it's similar. There's some places that get worse in precipitation, but it's relatively minor. So nearly everyone would be expected to experience less climate change if you believe the models. This slide just makes the same point. The other one is, we did this paper some time ago, and if you look at, and the idea is, oh, isn't this going to make international conflict? Isn't every country going to want a different amount? Well, in trying to optimize for both reduced precipitation and temperature change, this is done in terms of aerosol optical depth. but some countries would want maybe 10% more than the median and some 10% less than the median. But if you're trying to reduce for every country, everybody kind of wants right in this range. And so I think the idea that there's going to be all kinds of conflict over amounts. I mean, the conflict's going to be about doing it or not doing it. And I don't see huge conflicts over amounts. This to me is the main point, is that if you zero out emissions, basically temperatures stay high for centuries and they might even increase a little bit. And this is a composite of what, 1, 2, 3, 4, 5 volcanoes. And basically, with putting aerosols in the stratosphere, you cool the next year. And so, if you take these risks of deadly heat seriously, now the idea is that if in areas that become hot enough and humid enough that you can no longer cool your body, you can no longer cool your body through sweating because just it's so humid and so hot that you can't sweat fast enough to remove heat from your body, and is basically risk of mortality from heat. And so this is a map of under different RCP scenarios, number of days per year, where it's anticipated to get above these temperature thresholds, where being outdoors would be lethal potentially. And this is large areas of the tropics. And so if we say, well, look, we might be making large areas of the tropics effectively lethal, and cutting emissions doesn't give us any way to cool the Earth on timescales relevant to people who are alive now, the way we know to cool the Earth rapidly is through solar geoengineering. And so to me, the main scenario in which I could see solar geoengineering deployed is if these scenarios come about and these projections really are sound, and that there's risk of widespread death or widespread famine, and people in the tropics say, well, look, you in the north destroyed our climate, and now we have to do something to protect ourselves. And so the estimate for that the cost of solar geoengineering is relatively cheap. There was a paper, I think it was in Nature Climate Change 2 years ago, that estimated it would cost around $18 billion per year per degree of Celsius warming avoided. So, I think these numbers could be off by a factor of, say, even up to 5 or something either way. But let's just use that as a ballpark, that this is a kind of number that a coalition of countries in the tropics could get together and afford this. And so it presents a credible path for people in the tropics to protect themselves from excessive heat. Now, the other thing is, social systems, I think there's enough food in the world. People can grow food in the northern latitudes that nobody has to starve to death. We have air conditioners, we have indoors that people can engineer their way to safety if they have some resources. And so it might be also that solar geoengineering presents a credible threat, just that the tropical countries it would be within their resources to do this. It could well be in their direct interest to do this. And if the rich countries don't want to do this, well, then they need to give the aid to address the climate challenges by other means. So I'm trying to reverse here the paradigm. A lot of people see solar geoengineering as, oh, this is something that dreamed up by the fossil fuel companies to let them continue emitting CO2, and that, oh, you're only helping the fossil fuel companies by researching solar geoengineering. I see it completely oppositely, that this is a way of empowering the most disenfranchised people in the world and giving them some power to control their climate and maybe influence what the rich countries, how they respond to climate damage in those countries. So, yeah, so I guess I'll end there. Sorry, I went on way too long. But, the main thing is the last 2 points, that solar geoengineering is the only known way to cause the Earth to cool within our lifetimes. and the direct costs of solar geoengineering are low enough to be credibly undertaken by relatively poor countries in the global south. So, and so just to sum up here, that I think if we take climate challenges seriously, we should want as many options available as possible. And so, well, I think we can have arguments about what policy should be towards deploying these different technologies. That I would hope that we would be developing these technologies so that if people decide to use them at some point in the future, they'll be available. And I don't think we should prejudge what future generations might or might not want to do at some point in the future, but we should be giving them a full toolbox so they can decide the best way to address future problems. So I will stop there. I'll stop sharing.